This.
Playing all the exact instruments, or EDM producer who's not playing all the exact instruments, they're still making music that's expressing something based on the way that they set up the whole system. They're tuning the sounds, they're doing all these things. So there's always this bias that someone's putting in, and there's this larger social context which music exists in. There's the context of the performer and the audience, and the applications for algorithmically generated music. So far, algorithmically generated music has been more experimental, and people weren't so willing to pay money for it. But I think, sort of, also just on the complete flip side, like that's not really the approach we're taking Magenta, because we're sort of more focused on how do these tools create new opportunities for people to express themselves and create new types of opportunities for that type of interaction where you can identify, oh, here's this person that made this music, and I'm listening to their music, and this is what they're expressing to me. But they're expressing it with this new set of tools, with this new, with all these new technologies. So I sort of see it as more as just this continuation along the line of technology and music. I know a lot of you guys have seen the talk that this Q&A is related to, and I really like that metaphor of how music and technology has always been like intertwined, and that our oldest music technology actually outstrips some of our oldest, many of our other technologies, like still talking about pottery, like the flute is alluded to, because like the earliest phone flutes have that ancient history. So I sort of see this as part of that, sort of continuation.
It's a really helpful way to think about it. So our next question comes from our viewer Media Chris, who asks, how do you teach an algorithm?
Yeah, so we use the word teach, but there's really no, it's just a metaphor, right? There's really no teaching involved. Another way we can think of it is searching, that you can imagine writing an algorithm that you could, let's say, needs to find the best solution. You get 100 choices. You can try all 100 choices, and you give it a metric to say. The definition of what is good depends on the data that we presented. So we might say, do a good job of coming up with a set of rules that describes this data. But these rules are not hard-coded rules like if this, then that. They're more soft rules. So they're like, if you've seen these 10 notes in the past, like then give me a probability that the next note will be this note or that note, and then I'll choose from that probability to actually generate the next sound. So how we actually train the algorithms we generate, we collect a whole bunch of data that is the type of data that we're interested in modeling. So it might be a specific type of music or a specific type of melodies or drums or something like that. And then we use software that Google has open source called TensorFlow that basically sets up a whole possible set of computations to connect to make that prediction using these nodes. Functions that can map from this inputs to that output until it finds the best solution that it can find. And the analogy is, you can imagine it's sort of like like a slope or something where if a good solution is one that's really low down, and what we sort of the way we do the search is sort of equivalent to like doing a little simulation of physics where we just sort of make the solution traverse down the hill to find the basin of the most likely and the best solution of how it maps the inputs to the outputs. And there's more details about how we do that using backpropagation and chain rule and these types of things. But in essence, that's the idea. It's basically we set up a possible set of functions and we find the best function to map the things. So there's a lot of human choices there. There's the choices of what data do we use, what are going to be the controls at the end that the human's going to be able to control, and how do we set up the space of possible functions that it can search through, and how do we set it up so it actually searches through that, and then we let it search, and it usually doesn't work very well, so then we have to tweak the parameters, try again, and tweak the parameters, try again. So that's my day job. That's what we do a lot of time.
That sounds like a fun day job. So our user Eric W asks, what are your favorite bands?
So for me, I come out of a lot of improvisational music, actually, and so I know a lot of these things that we work on have more of an application to electronic music and stuff, but I'm a jazz guitarist and a rock guitarist, improvisational music, so I really like jam bands like Fish and other things like that. Actually, one of the coworkers that I work with, Adam, his cousin is actually the drummer for Fish, so we get to go to concerts together and sort of have that commonality, which is fun. But the people in Magenta really love a broad range of music. We have some people that are like classically trained organ players, and some that are just singer-songwriter, people that like pop music and play piano, and just people that don't do music at all and just enjoy machine learning and creativity.
Great. And our user Michael Novak asks, do you know Alan Holdsworth?
I know of, but I do not know personally in my experiences. I've been very fortunate to get to know a lot of fantastic musicians, but not him.
Okay. And coming from our viewer Konstantin Rosu, what do you think about Elon Musk's project regarding brain connectivity with machines? I think he's probably referring to Neuralink.
Okay.
Generally, that idea of connecting brains with.
I talk about brains more in interfaces more than Elon Musk's specific project, because I was doing a PhD in Berkeley for a long time, and interacted a lot with that because I was doing nanotechnology stuff. And there's it's a very interesting problem because you can do quite a lot with very little, because basically we have algorithms, right, that can find structure in data and map it to things. So like if you were to implant electrodes for, let's say, a patient who can't use, let's say, their arms or legs, and you want to let them control, like a robotic arm, just by thinking, there's no part of the brain that's mapped to, okay, this is how I'm going to control a robotic arm. There's nothing that was specifically learned over someone's history of their life to be able to do that. But what's amazing is that the actual biological brain is so adaptable that if you just take that signal and map it with an arbitrary mapping onto moving the arm around, you can get an adaptation where someone can actually learn to control the brain signals in such a way that it can make the arm move. Now, what's helpful is the signals that it's reading out of the brain are very coarse description of what's actually going on in the brain. So just a couple of electrodes sort of measure it. Sort of like if you were to take, I know a bunch of neuroscientists will have huge exceptions to this, but sort of like you're trying to understand how a computer worked by just sort of setting a thermometer inside and saying like, oh, it got hot here and it got hot there. It's a very rough measurement of what's actually going on. But then you can use machine learning to sort of refine that data and find the signal from the noise, such that there's this combination of machine learning, learning from the signal, and then brain co-adaptation, where the brain learns how machine learning has mapped that into moving an arm. And one of the most interesting things I found about those experiments was there was this idea that in order to get it to work, you actually had to cheat initially. the brain signals from the person's actual brain, but that reinforced these loops of like, oh, I'm doing it, and had someone's brain patterns change in such a way that they could actually do it later. So it gets into a wild and very still unknown world when you get into the biological brain in that way.
Interesting. And another question from the same user: can AI bring something potentially new for humans by kind of expanding our audio spectrum?
Yeah. I guess, definitely, right? It definitely, signal processing techniques in general can help us to hear outside of what we can normally hear. I have a friend of mine, Joshua Dickstein, who had this great PhD project that sort of was for helping blind people to see with echolocation. So we would actually have these sort of like cardboard ears that you would help people have, and it would send out ultrasound, high frequency sound waves, and then downshift them down into the spectrum that we can actually hear between 20 hertz and 20 kilohertz. So there are a lot of people who are not able to see can actually echolocate with clicks, by clicking and hearing the reverberations of how that reflects off the walls of the room. It's an amazing skill, and so this was this idea of extending that to being able to see much farther away than you could with just the frequencies produced by the mouth, because these high frequency waves could travel and reflect much farther. So that's like a very simple mapping where there was no goal in mind. There was no tuning of the algorithm based upon data or based upon how well it works for the participant. So you can imagine doing more advanced algorithms that use machine learning, which is tuning and adapting to the specifics of the situation, to the data, and the person's preferences and that type of stuff. So it definitely is a very interesting sonification. Those types of things is really an interesting application.
Our next question comes from our user C. Young, who asks, during the show, one scientist was worried about AI and robots becoming slaves if they become conscious. Do you have any of the same concerns?
Honestly, I think I have a lot of ethical concerns about the world, and there's a lot of things we could do to be better people and treating other people well, and AI can be helpful and hurtful in those regards. But I think we would have to, we're so far away from that level currently. Like, our models are so simple at the moment that there are much more pressing ethical concerns that are more about how we relate between each other as humans that we would have to tackle anyways before we get to that level of concern. So it's not that it's not fun to think about or interesting to think about, but I guess I'm kind of a pragmatist when it comes down to these types of things, and that maybe our time can be spent thinking about other things.
Thanks. And our viewer Jesse Theory says they love the computer's interpretation of what you played on stage during the program. Do you ever do concerts?
I do. What's interesting, I don't play with the algorithms as much. I find, like, during my PhD, this was on my side gig, so I would play a lot with computers and music, like, in front of others, but now that I do it as my day job, I find when I get home, I just kind of want to pick up an acoustic guitar and get back to very visceral, very sort of humanistic things where I don't have access to checking my email or anything like that. But hopefully, part of the Judge Project is really creating tools for musicians to use both live and production and all that stuff. And I think we have a lot of cool projects underway that should really help to popularize these technologies and make it a lot easier for lots of people to use this stuff. So hopefully, you'll hear some music sometime not in the distant future that you like because someone used some learning tools.
That sounds like it'd be a lot of fun. Our viewer Laws asks, do you think that arts created with augmented intelligence might cross the limit of comprehensibility for human brains? In other words, will there be a point where the only next step left for us are beyond us?
Yeah, this is the sort of other direction in terms of interpretation of music. Like, I've definitely done a lot of experimental music and like avant-garde lyrics and all that type of stuff, where you're sort of pushing a lot outside of a lot of the standard norms of like what we would call art, and then it brings up the question of like, what is this art? Which doesn't fit with these norms and all these types of things. And I think computers have the ability to go there. And right now, there's a lot of work people are making where they like personifying, the internal algorithm of a computer or something like that. That's in a way that is sort of unique and sort of almost incomprehensible. Like, there's ways of creating a lot of structure within sound that don't really have a lot of meaning to a human. That sort of sound like white noise, but there's still quite a lot of structure there. So I think the question, it definitely will be able to make lots of interesting new things. But I guess the question is, why are you doing it? Are you doing it just because you can do it, or are you doing it because you're trying to express something either for yourself in the process of making it and getting something out of that, or are you doing it because you're trying to express something to other people? And either something about the context in which you're making music or the performance of the music itself. And so it's sort of that postmodern question of like, you have to be, just because you have the tools to do something doesn't mean that you don't appreciate it. It comes to you will appreciate it either. So you have to have meaning brought by the people to the art, I think, in my opinion.
Our next question comes from Al Fanzer, who asks, what world-changing invention would you like to see 5 years down the road as a result of AI research?
Wow, that is a good one. I would really like to see, there's an explosion of data and of things that you can do computation on, and I would like to see better tools for helping people to understand the sort of space of thought that exists among people, and to understand sort of the truth that emerges from perhaps holding evidence for things, and just making it easier for people to actually understand where each other are coming from and communicate that clearly and see the way that their thoughts are contextualized in terms of the thoughts of others. And I think a lot of what we get right now is just sort of a barrage of a whole bunch of different opinions and thoughts and these types of things, but it's hard to connect to the human elements. And so yeah, sort of humanizing human in that type of way is something that I think having interpretable analysis of data and structuring of all this data that we're all producing as a society could maybe be helpful with.
Great, and this is going to be our last question for the session. It comes from user MSEMA500, who asks, do you enjoy jamming with AI as much as you enjoy jamming with other musicians?
No. Frankly, there's so many more levels of, I enjoy it in a different way, but it's a little bit more introspective. I don't worry about the feelings of the algorithm as I'm playing with it, and there's not this sort of social context in which I'm doing within, and there's sort of not this responsiveness that you would get from other people. And so that's not to say that that's going to be the same for everyone, and that that's always the case, but I find playing music with a bunch of human beings together is a unique way of communicating that sort of speaks a lot more than words can do, and it's a unique way to share your humanness with everyone around you, and I encourage everyone to do as much as possible if they can.
Well, thanks, Jesse. That's a great note to end on. We really appreciate you joining us today.
Yeah, thanks. This has been a blast.
Great, and thank you to all our viewers for joining us. We really appreciate all of your questions. And come back back in 2 weeks. We'll be talking about human regeneration and whether we can live forever. All right, thanks, Jesse. Have a great evening.
You too. Anyone who thinks they can talk about quantum mechanics without getting dizzy hasn't yet understood the first word of it. Does it represent you have a wave associated with part wave is spread out, part goes at a point.
If you want to work out what some physical process would be like, turns out intuition is not a very good way to predict what happens. Trying to reconcile those two accounts of what's going on makes it harder. The truth of quantum mechanics is that all these acts together in fascinating, beautiful mathematical
And that is one thing, experiment is another. We get to this incredibly dramatic conclusion that space is somehow a manifestation of quantum entanglement.
Now it's like we have functions.
The work that you guys are doing is starting to reveal a possibility that we might understand the fundamental structure of space itself. Good to see all of you. You see a quote up there by Niels Bohr, one of the founding figures of quantum mechanics. Anyone who thinks they can talk about quantum mechanics without getting dizzy hasn't yet understood the first word of it. Now, why would that be? What did Niels Bohr mean by that? Well, basically he meant that we all have a good intuition for classical physics, right? And by that I mean, if I was to take any little object, right, give it a catch, a nice one-handed catch right there, throw us a little bit further back, we go 2 for 2. No, we're still 1 for 2. They're still back in the dark. Here we go. Get that one over there. Good. Right now, each one of the people who caught, so that'd be the 2 of you over here, is a really evolved human being. No, you see, when we were out there in the savannah trying to survive, right, we needed certain skills. We needed to be able to know where to throw a spear, how to throw a rock to get the next meal. We needed to dodge some animal that was running toward us, and therefore we learned the basic physics of the everyday macroscopic so-called classical world. We learned that intuitively, and that's why when I throw an object, you don't have to go through some elaborate calculation to figure out the trajectory of that stuffed animal. You just put out your hand and catch it, right? It's built into our being. But that's not the case when we go beyond the world of the everyday. If we explore the world, say, of the very small, which is what we're going to focus on here tonight, we don't have experience in that domain. We don't have intuition in that domain. And in fact, were it the case that any of our distant sharp divide between the small and the big. We are big beings made of a lot of small things, so any weirdness about the small stuff really does apply to us as well. And in this journey into the micro world, the world of quantum mechanics, we have some of the world leading experts to help us along to figure things out, and let me now bring them on stage. Joining us tonight is a professor of philosophy at the University of Southern California, who spent 22 years at the University of Oxford as a student, researcher, and faculty member. He's the author of a book on the ever interpretation of quantum mechanics out of the emerging multiverse. Please welcome David Wallace. Also joining us tonight is a professor of chemistry at the University of California, Berkeley, co-director of the Berkeley Quantum Information and Computation Center, and faculty scientist at Lawrence Berkeley National Laboratory. She's a fellow of the American Physical Society and recipient of awards from the Bergman, Sloan, and Alexander von Humboldt Foundations. Please welcome Kay Brigitte Whaley. Our third participant is a professor of physics at the University of British Columbia, a Simons investigator and a member of the Simons Foundation Infra-Human Collaboration. He was a Canada Research Chair and a Sloan Foundation Fellow, and was awarded the Canadian CAPCRM Medal to Theoretical Mathematical Physics in 2014. Please welcome Martha Romstock. Our final participant is a professor of theoretical physics at Utrecht University in the Netherlands and winner of the 1999 Nobel Prize in Physics for work in quantum field theory that laid the foundations for the standard model of particle physics, one of the greatest minds of our era. Please welcome Gerard 't Hooft. Alright, so the subject is quantum mechanics, and part of the evening will involve some challenge to the conventional thinking about quantum mechanics. And so before we get into the details, I thought I would just sort of take your temperature, get a sense of where you stand on quantum mechanics. Is it, in your mind, a done deal? It's finished, you completely understand it? Is it a provisional theory? Is it something which 100 years from now we're going to look back on with a quaint smile? How do they think that that's how things work? So David, your view.
Well, I don't think we fully understand it yet. I think it has a lot of depths left to come. And who knows, it might turn out to replace, but right at the minute, I think we don't have either empirical or theoretical reason to think that anything will take place.
What are you doing?
I think it's here to stay. There may be modifications.
Here to stay,
Here to stay. There may be extensions, modifications. There may be something more complete, but this will still be part of it.
Okay. Yeah, so there's a frontier in quantum mechanics. And we don't know if we're going to have to modify quantum mechanics, or it'll all be the same quantum mechanics, but so yeah. Now, Gerard, you have unusual views.
Well, yes, I want to spend the rest of the explaining to my mind, quantum mechanics is a tool, a very important mathematical tool, to calculate what happens if you have some underlying equations.
So, just a quick overview, we're going to start with some of the basics of quantum mechanics, just to sort of make sure that all of us are more or less on the same page. We'll then turn to a section on quantum measurement problems, something weird, quantum entanglement, as in the title of the program. We'll then turn to issues of black holes, space-time, and quantum computation, which will take us right through to the end. All right, so just to get to the basics of quantum mechanics, the story, of course, began more or less in the way that I started. We understood the world using classical physics in the early days, way back to the 1600s, and then something like, we started with Newton, of course, and we move on to people like Max Planck, Albert Einstein. What drove the initial move into quantum physics, David?
I think it was really just pushing really hard at classical mechanics as it went down into the scale of atoms and the structure of atoms, and just finding that structure snapped and broke, that trying to use classical mechanics to understand how hot things got or how electrons went round atoms without collapsing into the nucleus. In all those places we had a series of hints that something was amiss in our classical physics.
Yes.
And it took, I guess, most of 30 years for those hints to coalesce into a coherent theory, but that coherent theory then became particles, fields, made something gravity, and the language was more or less sort of solid, like, I guess, about 1930.
Yep, and it's actually quite remarkable that it only took that number of years to develop a radically new way of thinking about things. And Richard Feynman, who is, of course, a hero of all of us, also known to the public, famously said that there was one experiment. We could go through the whole history of everything that you described, with the ultraviolet catastrophe and photoelectric effect, all these beautiful experiments, but the double slit experiment, luckily for us in having a relatively brief conversation, allows us to get to the heart of this new idea where it came from. It's actually the paper on, in some sense, the double slit experiment, the first version of the experiment. I'll draw your attention to what you see the word aspect, and this is just a footnote, but in the old days, people would actually describe why now something went down in a scientific paper, but as science progressed, we were kind of taught, no, don't ever say what went wrong, only talk about what went right. But here's an old paper, and indeed this experiment emerged from an accident in a laboratory at Bell Labs. They were doing a version of this experiment, they turned the intensity of the light from quartz to shear, and they did the experiment unwittingly. They changed the experiment to something that's actually far more interesting than the experiment that they were initially carrying out. So just to talk about what this experiment is in modern language, I think we can just what's the basic idea of the double slit experiment?
So you take a source of particle of any kind, below light, for instance, you shine that light in a narrow beam on a screen, it has two gaps in it, and you look at the pattern of light behind the two gaps in the screen. It's just literally gaps in a black sheet of paper, for example. But the light going through, if light is a particle, you'd expect one sort of result on the screen. If light is a wave, you might expect something different as the light comes through one particle slit, interferes with light going through that particle slit. And the weird thing about quantum experiment is that it seems in those ways we did both of those things at the same time.
Good. So, Brigitte, if you can just take us through a particle experiment to build up our intuition. So let's say we carry out the experiment that David described, but we don't start with photons or electrons, we start with pellet bullets or something. So I think we have a little animation that you can take us through. So what would we expect to happen in this experiment?
Well, we have the source of the pellets here, one minute. Putting out the pellets, and some of them go through the holes, and the ones that go through the hole, they sort of travel rectilinear, straight ahead, as we might expect from a classical intuition. And we get two bands at the back, indicating the pellets that went through the right slit on the right, and the left band is the pellets that went through the left slit.
Now, if I was, that's completely intuitive, right? So this is the stuff that our forebears would have known even on the savannah, right? Now, if we took the size of the pellets and we dialed them down to a very small size, before going to your quantum intuition that you have, what would you expect naively to happen if you simply dialed down the size? Would you expect there to be anything different if you were... this is a leading question, by the way. Just follow me here. The answer is, would you expect anything different? I expect anything different. No. So there we go. Naively not, exactly right. So here's what you would naively expect would happen. Again, you got the particles going through the two slits. So Mark, tell us what actually does happen. Not that I don't think Brigitte could just give us all a little airtime. That's kind of wow, the place where you would least expect to see something on that screen is exactly behind that big barrier that's in the middle. Yep. And somehow, when you actually do the experiment, you see that actually that's where most of the particles end up. So it's exactly the opposite. And then you get this weird pattern with other bands going out, and so you initially would stare and shake your head and wonder what happened. So we'll analyze what that means in just a moment. But we often, I don't know, probably almost everyone in this audience has seen a still image or an animation like this in discussion of quantum mechanics. And I thought it'd be kind of nice to show that this actually happens. It's not just animation that artists does. So we can actually do the double slit experiment for real right now. And to do that, I'm going to invite a friend of mine from Princeton University, Omaran. Can you wheel out, if you would, the double slit experiment? Alright, so what we have here is laser on this far side. So this is our source. Actually, we're doing this in some sense opposite to the orientation that we saw in the animation. And we're going to fire this laser, which is photons in essence. And the photons are going to go through a barrier that has two openings in it. It's hard to see them, of course, mechanically, but trust me, there's a barrier with two openings. And we're going to take a look at the data that falls on a detector screen, which in the modern age is a more complicated and somewhat finicky piece of equipment. So we're all sitting here on stilts, if you speak any Yiddish, you know exactly what I'm talking about right there. But hopefully this will work out. So Omar, why don't we just actually see ambient noise? Can we see a little bit of that first? Can we switch over to the input to the screen? Right, so this is the output for that device. And now if we actually turn on the laser and allow us to collect all the photons that land, they're building up. And there you see what actually happens. This is the result of this very device here. And you see it. We have you can see on the very far left, we see some of the photons are landing. Then we get a dark region in between, then a bright, a dark, a bright, a dark, a bright, a dark, and a bright, and a dark, even though this device over here really is a barrier that has only two slits in it. So the animation that we showed you actually does hold true in real experiments. And that then forces us to come to grips with it, to try to understand what in the heck is actually going on. So thank you all much. So there we have it. We have this situation in which we expect to get two bands and we got more. What does that tell us? Where do we go from there? There's an existing bit of mathematics that comes up with exactly that same pattern. But it has nothing to do with particles. It's the mathematics that you use to describe waves, water waves, other kinds of waves. Yeah, so can we see the animation has a single. So this is a warm-up to the problem where we have water going through a sink opening. Just tell us what we see happening here. That's right. So you've got sort of a water wave, a wave coming along, and then that slit acts as a bit of a source for this rippling wave going out in a circular pattern. And you see it's most wavy at the plates behind the slits of the wall. That's indicated by the brightness there. Yeah, and then if we go on to a more relevant version for the actual double slit experiment. Yeah, so now we've got that same wavefront. But now there's two slits, and it's like there's two different sources of waves, like if you threw two different pebbles in the pond at the same time. And then what happens is that they're both creating waviness. But some places on the screen, the wave from one is doing this, and the wave from the other is doing this, and they kind of cancel out. But right there in the middle, what's happening is that the wave from the one slit is going up, right when the wave from the other slit is going up, and then they do this, and you get a big wave, and that's the bright part. But if you work out the mathematics, then the places that have the big waves are exactly these forced into, as they were saying, not just thinking that a large collection of particles behaves like a wave, which maybe not wouldn't be that surprising because water waves are made of H2O molecules, particles, and therefore they're kind of wavy. But each individual particle somehow has a wave-like volume, and historically people struggle to figure out what wave, what kind of wave, what is it made of, and what does it represent if you have a wave associated with a particle. Wave is spread out, particles at a point, and it was Max Born in the 1920s who came up with the strange idea of what these waves are. So, Brigitte, what are these waves telling us about?
Well, the waves are, what we see is the probability, which is the square of the wave, or the modulus of the wave.
But so here's a wave behind you, so you said probability.
Yes.
In essence,
This is an amplitude. This is an amplitude which will give us the probability. But if we take this amplitude and look anywhere here with some measuring device, we will find with some distinct probability after measuring any time. Now it's the probability that would all appear on the left or all on the right.
So in some sense, vaguely, where the wave is big, there's a high likelihood you're going to find the particle. Where the wave is near zero, there's a very small probability that you're going to
You
find
can't
the particle.
guarantee it. So any one particle would be in a place where the wave is very, very small.
Now these are all just pictures. In the 1920s, physicists were able to make this precise. So Schrodinger wrote down an equation. I think we can show you what the equation looks like. Obviously, you don't need to know the math to follow anything that we're talking about here. But Gerard, you wanted to emphasize that there is math behind this because your experience has been to make people miss the point. So feel free to emphasize.
Absolutely. Quantum mechanics, when we talk about it, there's a temptation to keep the discussion very fuzzy. And so I get many letters from people who have their own ideas about what quantum mechanics is, and they are very good in reproducing fuzzy arguments, but they come without the equations, or the equations are equally fuzzy and meaningless. Whereas the beauty of quantum mechanics is the fundamental mathematical coherence of these equations. You can prove that if this equation describes probabilities exactly as you said before, then actually the equations handle probabilities exactly the way probabilities are supposed to be handled. Except, of course, when two waves reinforce each other, the probabilities become 4 times as big rather than twice as big. But another shot spots the waves annihilate the probabilities, and so the probability becomes 0 where the waves are vanishing. So it all this hangs together in a fantastically beautiful mathematical
Now, math is one thing, experiment is another. So how would you test a theory that only gives rise to probabilities of one outcome or another? How would you go about trying to determine if it's right or it's wrong? Yeah, so it's like if you gave me a coin and you said, this is a probabilistic thing, you flip it, it's going to be heads half the time and tails half the time, and I want to check that. I don't trust you. I don't know why that would be, but so I just flip the coin, 100,000 times or whatever. A lot of things. The more sure I want to be, the more I flip it. So maybe I do it 10 times. I get 4 and 6, and maybe I'll flip it 100 times, and then I get 48 heads and 52 tails. So I can basically just repeat the experiment a whole bunch of times. And if I have a very precise prediction from those quantum mechanics equations to tell me exactly how often I should expect to get one result versus another. Well, I think we can give you a little schematic. What do we say? So that's, in some sense, really the basics of quantum mechanics. Classical physics, particle motion,